starting in 2 minutes. Please hold on for 2 minutes. So good evening everyone and welcome to this webinar of Hexstar Universe. Today's topic for the session is remote sensing, and the speaker for today's session is Sushanth Seepana. He is currently pursuing M.Tech on remote sensing from IIT Bombay. So without further ado, I do request Sushanth to start with today's session.
Uh, Hi guys, am I audible and visible, right?
Yes.
Okay, sure. Thank you all for taking your time and joining in. Uh, I'll just I'll just start without any. I'll just share my screen. Give me a moment. Is my screen visible, right?
Yes.
Yeah, it's in the presentation mode as well.
Yes.
Okay, just a minute. Uh, okay, okay. Uh, sure. Hi all. I'm Sushanth Seepana, and welcome to the session for Seeing the Unseen, an introduction to remote sensing. I'll start the session with a brief introduction of myself. I'm Sushanth Seepana. I'm currently working as an assistant manager business development at Adani Green Energy Limited, and I did my masters from IIT Bombay in remote sensing with a B.Tech Civil from GVP College of Engineering. And my achievements are that I secured AR4 in gate geomatics, and I've been a B.Tech gold medalist as well. So, given a small brief intro about myself, we everyone has a vision for themselves. So, I also envision something myself uh, in a professional sense. So that geospatial for greater good. We always, whatever we do should be helpful for bigger thing. So with this vision, and coincidentally, today is also Earth Day, and let's take this moment or this event as a chance, and let's all together pledge that we'll work for a sustainable and habitable Earth in the way possible. Okay. Before that, I just have a small poll for you guys. I just posted the link for the poll in the chat. You can open that and you can start putting the poll, or you can scan the QR, or even you can open Slido browser slido.com and you can enter the code. I'll just take 2 minutes. Uh, you can start putting your answers in this. This is for me to have an idea of the audience and to take the thing, tone of the meeting. Uh, 1 more minute, guys. We'll just who are on the call, put your answers. Cool. So pretty much most of the people they have an idea of what remote sensing is, but not that much. So not those many people are very less aware. So people are aware of this. This is a good thing. And what we'll do is that we'll go more technically into this. And yeah, so one of the some of the answers are there. It's just Google Earth images, right? Yes, that is the perception we always had when we really don't know about remote sensing. We always had this image that okay, satellite images, but Google Earth images. So this is how this is a Google Earth image or Earth as viewed from space. This is a cloud free image, but most of the times there will be clouds, but this is a cloud free image. But let's see how it looks through the eyes of a satellite. This is a satellite called EOS-6 or OceanSat, and the sensor that is looking is this, the data, the image formed through the sensor is OCM3, Ocean Color Monitor. So this is how Earth looks for this particular sensor. And there is one more satellite called ILSAT 3DS, which is a weather satellite, and Earth looks in this way. So here I'm just pointing it out. All this orange color thing, these are clouds. So how is this orange color coming, and how are those clouds? We'll be going deeper into those with these sessions. But this is remote sensing is something which is not visible to the human eye. So that's why the session is also I decided to name the session "Seeing the Unseen." We'll with this introduction we'll get more into this what remote sensing is about. So this is how the format or the flow of this presentation is planned. We'll go ahead. Yeah. So what is remote sensing? Remote sensing is acquiring information and making inferences from objects and measurements without coming into contact. Remote and sensing. You sense an object at a remote way. Let's take an example. Here we have a mango. We have some mangoes. Without touching it, you can understand. Okay, the left one is unripened and the right side one is ripened. How? Either we see it with the color or we smell it. If it's physically there, you smell it and you understand it. Okay, this is ripened. This is unripened. So you're not getting into the contact. In the same way, the satellites also operate. The satellites fly at an orbit and they sense the Earth surface and they start imaging. How are these two? Let me draw an analogy between these two. So when the light from an object reaches your eye, the retina and all they capture the information and they send it to the brain, and the brain processes it, and you understand. Okay, this is an animal, or this is a mango, or this is ripened mango. You understand it. In a similar way, the electromagnetic energy, which is nothing but the light energy in the above example, it reaches the sensor element. Here, the sensor element is retina for an eye, whereas for a satellite, you have the sensor. And this sensor captures the data and sends it to the ground station. So ground station is the processing unit here, which is in similar terms to the brain. The ground station processes the data. Once the data is processed in both the cases, you get one thing is common for both of them, that is image. And from this image, we draw inferences and we get information. The brain does it on its own, whereas in the case of remote sensing, we either have to deploy a system, writing a few lines of code and automate the process, or we need to employ a person who does extract the information. So one more extra hand is needed here in the case of remote sensing. Now we understood what remote sensing is. Let's define it. And this is one of the definition used by United Nations, that sensing of Earth's surface from space, utilizing the electromagnetic radiation from the objects for a given purpose. So I highlighted three things: space, electromagnetic waves, and sensed objects. So space, when it comes to space, it means the satellite or the sensor that's present from space. And with electromagnetic waves, we mean the electromagnetic energy. And objects, which are the target, when converted, would be the image. So these three are the three basic components that form the remote sensing system. electromagnetic radiation, satellite, and then image. So at a glance, we see this is how remote sensing is done. We have sun, the energy from sun falls onto the surface, it reflects back, the satellite captures it, it is sent to the ground station, it's processed, and you get an image. So this is the entire process of remote sensing. And remote sensing is of two types. One passive remote sensing, one active, two active remote sensing. Passive remote sensing. You do not employ any your own electromagnetic, your energy source. It's that the energy coming from sun is being used passively. You can understand this in a different you can see it in a different way, like you're moving ahead with a torch. One, you're moving on a road and you just have a sunlight, but when it's night you utilize a torch. So here you're having your own energy source. In the similar way, satellites, some kinds of satellites, they employ their own energy source, they send the radiation, they capture back the uh, reflected radiation. These are active remote sensing satellites. And whereas passive remote sensing satellites, they completely rely on the sun's energy. These can't work in the night time. Passive remote sensing. Whereas active remote sensing, they can work both during day and night because they have their own energy source. This is remote sensing at a glance. Now we'll go into the three parts. As said, electromagnetic energy, satellite, and image. The first thing is electromagnetic spectrum. So for remote sensing to happen, we need a medium. The medium here is the energy. It could be any energy, electromagnetic energy, which is light or any gravity or sound energy, any kind of energy is required. So this electromagnetic radiation, or this is the continuous spectrum of different wavelengths. Here we have short wavelength from gamma rays. We have short wavelength to radio, ranging to radio waves with very long wavelengths from nanometers to hundreds of meters. We have a wide spectrum here, and this entire spectrum, all these waves are currently existing in nature. Only thing is that we cannot see. What I can see only this very narrow wavelength ranging from uh, 0.4 micrometers to 0.7 micrometers. The wavelengths are not written here. So it's like 400 nanometers to 700 nanometers. Only this very fine range can be captured by eye. So your eye is a sensor which can capture this particular range of wavelengths and can process it. So your eye is a sensor. In the similar way, other satellites or sensors on board other satellites as well, they work on a particular range of wavelength. They capture the data and then they process them. So a particular range of wavelength is referred to as a band. So we call this as a blue band, giving this given the wavelength from ranging from blue, and this is the green band, and this is the red band. So we have different bands, which means a range of wavelength is designated, and this band can vary from satellite to satellite. That I will be discussing in detail. But right now, what we can conclude is that satellites work on satellites. They employ sensors, and each sensor works on a particular range of wavelength, which is referred to as band. So this is something about the physics of the remote sensing. Now let's understand how do satellites really look at Earth. So this is an image. This is my college, IIT Bombay, and this is a satellite image, Google Earth image. Let's say. Now let us assume that we are flying, or you're flying on a very, let's say you got a drone, or you imagine yourself flying. We could see the completely captured, like you understand, okay, this is a building, there is some construction going on here, okay, there is a swimming pool, or there is a ground here. So these are things you're very much able to understand. There are a lot of buildings, there is water here, you're able to comprehend, which means this range, all the energy or all the light that is reaching is from the visible region. And let's say how the satellite in a visible region works. This is something as comprehended by human eye, right? Let's see how a satellite sees. So this is an image of the same area from a satellite called Sentinel-2, which has a spatial resolution of 10 meters. If you can see, all the images here are pixelated. They're lot pixels. You can see the pixels as well, which means the 10-meter pixel, all the energy from the 10-meter pixel is captured by the sensor. So this is this is one image. Let's see how different bands of the satellite look. So this is an image of the blue band. So you see, it's like just like black and white values, you just white values with high reflectance and black with very less reflectance. So this is how you see how a satellite in a blue band sees. Next, this image is from green band, and this is from red band. But human eye, we see the entire visible range, right? Blue, red, green, blue. So this is to see it in human eye. So what human eye does is that it it stacks the three bands. It sees in red wavelength, it sees in green wavelength, it sees in blue wavelength, and it stacks three of them, which is called a natural color composite. RGB is a natural color composite. You have the red band, green band, and blue band stacked upon, and you see this. So this is how it's comprehended by human eye as well. So this is a natural color composite. Let's see how satellite sees in other bands as well. This is a near infrared band. In a near infrared band, the satellite captures the infrared waves. In infrared, you see the water is like completely and very clearly distinguishable from the other parts, which means water has very less reflectance in the infrared region. So this is how we understand the physics. We understand the physics of it. Okay, particular object, how does it reflect, or how does it behave in for a particular wavelength, and then we comprehend the image. This is a near infrared image, and this image is a short wave image. You can see the pixels difference. This is more blurred, as in the pixels are bigger. Here the pixels are smaller. The difference is that here the satellite image works on bigger resolution, which means it captures energy from a bigger ground resolution. Here it captures from 10 meters, whereas this captures to 20 meters. And if you see the next wave, this is an aerosol band, and this is in 60-meter resolution. You can see the pixels very clearly, but somehow the pattern remains same. This, which is white here in this shape, in this the shape of the pattern remains constant. Sometimes from band here the pattern is remaining constant, but it need not to be always that the pattern remains constant from band to band. It can be a completely different pattern as well. So in this way, these are all different properties. I told a lot of words: band and then resolution. You see, 60-meter, 20 meters, and all. So let's. I'll I'll discuss them in detail on going forward. But this is how a satellite views, and this is from one satellite. Let's see a different satellite how it views Earth. And this satellite is called INSAT 3DS. It is a weather satellite which operates for the Indian region. This captures the visible. VAS is that visible spectrum. So the entire region from red, green, blue, all the wavelengths ranging from 400 nanometers to 700 nanometers. All things are captured, and this is how the image is formed. If you capture them individually and stack, you get a natural color composite, which is a human comprehensible image. But if you combine all the images, and if you see, you always get a black and white or a panchromatic image, which is this image. So this is how, since the clouds are white in color, and this is how we see. We can see there are a lot of clouds here in the visible, and in shortwave infrared, you see them as a gray color, whereas in middle infrared, you see them completely uh, in a black color, which means they're not at all reflecting in. They're not at all. They're completely absorbing the light infrared region, infrared waves, and these are different bands. And if we stack some of them, we get this image, which is a false color composite generated by stacking visible, shortwave infrared, and then mid infrared. Combining these three images in a RGB format, you get this color image. So one, you understand natural color composite, which is RGB, and any other combination other than RGB. You put BGR or any or visible shortwave or any other combinations of band is always referred to as a false color composite. So this is how satellites look at Earth. Now, now let us go ahead. Now, simply putting everything back in a order, we have a platform on which satellites and sensors are onboarded, and you capture the target on Earth. You get back the information, you process it, and you generate which means the output is the imagery, which has which is of analysis part and the applications part. So this is satellite remote sensing system at a glance. Now let's understand, since we already discussed about platforms, let's go in detail with each of them and see what it is. Sensing platforms. In sensing platforms, hope guys, I am clear till this part. You have any questions? You can put in the chat. I'm just monitoring the chat as well, or you can put them in chat. I can answer in in the last as well. So I'll start with the sensing platforms. So the sensing platforms, sensor systems, they need to be on a particular platform at a particular height, so that the imagery is constant. You move at a different height, the scale of the image, uh, how it's being viewed, we can't understand. So you fix the platform at a fixed height, and platform can be any of the following. Let's see, there are a lot of platforms shown here. One, it can be ground based. You have a camera, or you have a tripod mounted on a ground or on a tripod stand. And next you have drones, some hundreds or till kilometers of height. Then you have some airships, or you have satellites which are around the height of 100 to 1000 kilometers. And then there are these geostationary satellites which are at more than 10,000 kilometers of height. The INSAT example, the weather satellite example, is at 1,000 kilometers of height. And earlier, I mentioned that the passive remote sensing satellites, they cannot work in night. So what the scientists suggest is that when you can't see at night, why don't you play with the orbital parameters and ensure that whenever a satellite passes through a given point, it always has sun, and then the concept of sun synchronous orbits arrived. So these are some near polar orbits in which they cross the given area at a very constant time. Let's say if it's crossing equator at 10:30 a.m., it crosses that particular place at that equator every time at 10:30 a.m. In India, if it crosses at, let's say, 12 p.m., it always crosses at 12 p.m. Or at some other place, it crosses at 1 p.m., it always crosses at 1 p.m. So in this way, the sun synchronous orbits are defined. And synchronous orbits, high altitude, fixed towards Earth, near polar orbits, close to Earth, and they have longer revisit. I mean, it's frequent revisiting. And I just have I spoke a lot about this, but to have a visualization for this, I'll just play a small video. Just a moment. Yeah. So the video starting playing, you can see how the satellite is moving. This is a constellation, which means two satellites. You have two satellites rotating, and you can see the timestamp how it's moving. And if I could just pause the video and just sorry, just play the video again. Just give me a moment, guys. Yeah. So you can see this. Within 5 days, the entire Earth will be covered. So when you have a constellation of satellites, let's say you have fewer number of satellites, you can cover the Earth more frequently. When you have fewer number of satellites, it takes time. It also depends upon the orbits as well. Yeah. So coming to sensors, questions in the chat. There are some questions. I'll just put them to the end. If you don't mind, I'll just go with this. In the meanwhile, if your questions are answered, it's fine. If not, I'll just keep them to the end. So we understand the satellite and the orbit. Now let us come to the sensors part, because sensors are eyes. You just have this. Without eyes, these are the main things. The sensors. So sensors are instruments that measure the electromagnetic radiation, and these are referred to as remote sensors or sensors. So these are classified into two types. Again, passive and active. This comes from the sensing methodology. And passive sensors are of two types again. One, work in the visible and infrared region. Two, uh, let's just see. Second is that microwave. Now coming to visible and infrared, we have multispectral, hyperspectral, and thermal. What is multispectral? What is hyperspectral? I'll be discussing it within few slides, but you understand multispectral and hyperspectral are part of optical or visible imagery. You see them with human eye. You can, whenever you see a multispectral or hyperspectral image combining with the bands, you understand without any further analysis. But when you see the thermal band, you need to make inferences. You need to do more processing. Thermal is uh, works in the infrared, where infrared region. And passive, this is about visible and infrared region. When it's microwave region, you have radiometers. You see microwave, and initially what microwave is that when microwaves, each and every body emanates some microwaves, or they reflect the waves that present. So without any own source of it, the reflected microwaves are captured by these radiometers. These are usually utilized for weather capabilities. Radiometers or sounders, these are used for weather capabilities. Visible and infrared, these are for natural resources management or land. And this, the applications will be said covered in more detail, but these are the sensors. So passive sensors are visible and microwave. In the same way, active sensors are also visible, which are lidar, and microwave is synthetic aperture radar. So what is lidar and synthetic aperture radar? Instead of seeing it from the sunlight, you have your lidar stands for light detection and range. You have your own light source. You send it over the image. You get a point cloud of data. You process it and then you infer the images. This is how it works for the lidar in the visible region. For the microwave region, you have SAR images. SAR images is synthetic aperture radar. You send the microwaves, they reflect back the surface, and then they hit back to it. Now, basically, it's passive and active with visible and microwave in both the cases. Now, let's see how SAR image. Now, I talked about a lot of images of optical images, but to give an idea of how active remote sensing or uh, other ways how sensors look, here is an image of SAR imagery from a satellite called RISAT or EOS-4 of the Indian ISRO satellite. So this is a HH polarization, which is both horizontal. The polarizations is a little more technical. Just keep it that this is similar polarization. It's a horizontal polarized light. So this image is an image of Chennai city, and this area is the lake, or which is this in dark black color is the Pulicat Lake, and this is the southern India, basically Chennai. The urban area is reflecting very much bright here, and the small white dots in the sea. This right side image is the sea, and the small white dots are ships. So this is how you can utilize SAR images for ship detection as well, and oil spills. There are a lot of applications with the SAR images. We can see in the application part in the this part. Similarly, you have it's a different polarization. You send horizontal polarized light and you receive vertical polarized light. So it's in a different polarization. It's like different. The polarization part, I'll just keep to that part. I'll not go into more details of this. So when the polarization of the light energy changes, the image completely changes. Here you can see the other areas are also bright as well. Here compared to the other regions, only the urban areas, apart from the urban areas, the other ones are little darker, but here the other areas are brighter as well. So this is the polarization effect. So combining these multiple polarizations, you can give it different images and you can extract information. So this is about the sensors and multiple sensors, one optical sensors and SAR or microwave sensors. So what are the characteristics of these sensors? Information, whenever a sensor collects, it depends on this instrument to detect the small differences in emittance or reflectance. So there are 4 things highlighted. 1, difference in emittance or reflectance. 2, number of spectral bands. 3, as small as an object. And 4, as often as possible. So these 4 can be translated as the characteristics. 1, spatial resolution. Means how much does each pixel measure on ground, or how small an object I can identify. This refers to the spatial resolution of a sensor. Spectral resolution. How many bands or how many ways I can see an image, and how many bands can I detect a place. This represents the spectral resolution. And radiometric resolution is how many levels of intensities the sensor can measure. And temporal, which means how frequently I can look at the same location. I mean, my satellite can move and come back to this. At a moment, this comes like all of a sudden. I mean, it can be too much, but I'll just walk you through in detail through each of the spatial, spectral, radiometric, and temporal resolutions, and you'll get a good idea of it. So let's understand what spatial resolution is. Let's say we have a lake or a polygon in a blue color. If a sensor has a 5-meter resolution, it can it can see or it can capture the energy from this in very finer number of pixels. There are a lot of pixels here, but when you come to 10-meter resolution, the number of pixels are reduced. So the information you gather more information. So the fineness, let's say inside this there is a small chip which you can detect, which is a chip of 5-meter size. You can detect with 5-meter resolution data, but with 10-meter resolution data, you can't understand. You can't detect a chip that is less than 10 meters. So the resolution number 5 meter or 10 meter or 30 meter, which means that any object smaller than this value can't be detected. The initial Google Earth imagery, when you're able to see almost very clearly, which means it's sub-meter, 30 centimeters. I mean, if you put a scale or something cannot be visible, but anything bigger than a scale, you can see it very clearly. So if it's 30 centimeters resolution, any spatial resolution means what is the smallest object you can see, smallest object size that you can detect from the sensor. So, and smaller cell size, which means higher resolution. When we say higher resolution, high resolution data, the pixel value will be very small, 0.3, 30 centimeters or 1 meter, 5 meters. When we say lower resolution, it means 1 kilometer or 30 meter, bigger data. So this is spatial resolution. So it is a measure of sensor's ability to how closely the objects are distinguishable. So this is a theory part of it, but how you see the images. So here is an example. In a near infrared, you can see the image is less pixelated, but coming to this, it is getting more pixelated. So this is how the spatial resolution comes into picture. First image is 10 meters, second one is 20 meters, and third one is 60 meters. And coming to the question, we cannot change the resolution. What we can do is that when we launch the satellite, we fix a particular resolution to it. Okay, this satellite, this works in particular resolution only. If you want to do it in a different resolution, we need to have another sensor on another data getting the sensing in that range. The resolution or the characteristics of sensors are prefixed before a satellite is launched. So these are the varying spatial resolutions for a Sentinel-2 image. Already discussed the Sentinel-2. So different bands have different spatial resolutions. And one more example is that we have soil moisture data. Soil moisture data. This data is sensed from radiometers. Radiometers, if you remember, it comes from the passive microwave. Visualize this. What are these bands and this thing? I have another imagery comparing various resolutions. You can see the wavelength range here. And this particular thing, let's say I have a Landsat 8 satellite. So this two, band number two, this operates with uh, this particular range of wavelength. Band number two, which means it zero point 0.5, and band number six, with this is a central wavelength, and band number seven, it takes this entire wavelength range and it captures all the energy from this particular wavelength. And this is for Landsat 8. We have different other sensors as well. Sentinel 2, which we seen, the blue, the green, and red, different images. And there are other satellites as well. So how fine if this if the if the bands are too fine, you say the spectral resolution is high. If the bands are too wide, you say low spectral resolution. Here you can see this is of a low spectral resolution because this is covering a very large number of wavelengths, whereas this is having a very fine wavelength. So you can see that that's what I was just showing here in the that's what I was showing here in hyperspectral. You have a lot of bands, continuous bands, and very fine bands as well. In multispectral, you have broad bands. So, which means the spectral resolutions are wide. The spectral resolution for multispectral is less. For hyperspectral, it has high spectral resolution. So, spectral resolution band, the the band range. That's what we define the wavelength range. So spatial resolution, object, you understand the object, the size of the object. Spectral resolution, the wavelength. Spectral resolution is simply put the wavelength in which the particular sensor is operating. And coming to radiometric resolution, all these images are captured in this is electromagnetic radiation. You need to transfer this or store this image in a digital form. So you need to convert this. The energy values is quantized to a particular level, and this quantization process is referred to as radiometric resolution. So the energy is divided into a number of discrete levels. So to put in this, let's say if it's a 2-bit image, you either put as a black or a white image. In two bits, which means there are 4 levels, 2 to the power 2, 4 levels, you have colors of image. And going the number of higher number of bits, the finer the levels are. So you can represent a large range of wavelength. So larger the wavelength, the imagery would be more clear to understand. How is this happening? So radiometric resolution is electromagnetic energy being quantized into a particular number, into a digital number. And how is this conversion happening? And you can see this with an example comparing with two larger number of with different radiometric resolutions. Given an area, if it's captured with a 2-level radiometric resolution or 2-bit quantization, the energy you say, okay, energy less than 100 wave, some Landsat is able to cover in 18 days. This is because MODIS has a higher swath width, or the spatial resolution is 1 kilometer. So it can cover, let's say, thousands of kilometers in one revolution. When it can cover thousands of kilometers or hundreds of kilometers in single revolution. So the entire Earth can be mapped in single day. Let's say it takes 1.5 hours or 2 hours. In 12 times, it can cover the entire Earth with some overlap. Whereas coming to Landsat, it has a swath width of 150 kilometers. If it's 150 kilometers and the perimeter of Earth is like 2 pi into 6,400 kilometers, and this entire long thing, it needs to be covered in lot of intervals as shown in the previous animation. You saw the satellite, how it's covering, and it's taking some time, 5 days or 10 days to cover the entire Earth. In this way, temporal resolution also is dependent on the swath width or the spectral or the spatial resolution. How large area you can cover within one single revolution. So temporal resolution and the swath width are kind of linked, which also defines the time way. So just to summarize, spatial resolution, how clear the image would be or how clarity you can see. Spectral, you understand what are the different bands. Is it viewing in very finer bands, or it's conveying the information from a large wavelength region? And spectral, second step to the spectral is the radiometric. You detect the energy, but when you detect the energy, you have to convey it, you have to store it as an image. So how you are quantizing it? Let's say energy was of some 100 radiance value. How is it converted or stored as a radiance as a digital number in an image? This quantization depends on the radiometric resolution. And temporal resolution, how frequently it can be. All these four are the key characteristics for any sensor, based on which I think you can understand more about the how a satellite views and what are the various characteristics attributed to it. Now, given this understanding, I would like to talk about few missions, various Earth observation missions. Uh, so EO missions, they are conducted from various space organizations, and they play a very crucial role in understanding the planet's environment. So what are these? These missions, they collect valuable data on land, ocean, atmosphere, and organizations such as NASA, ESA, European Space Agency, and ISRO, they are leading the Earth observation missions, and they have a wide array of information that is currently here. Can you guys just excuse me for a minute? I'll just be back. Just excuse me for a minute. I'll just be back. Oh, sorry for the interruption. Yeah. So there are a lot of Earth observation missions. So coming to this NASA. So we have a fleet of satellites. SMAP, soil moisture. Uh, it's a mission related to soil moisture. It captures in the passive microwave region, and you understand the soil moisture as an example shown. CloudSat. This works on the clouds. It understands. TRMM. It captures rainfall. And GRACE, it captures the uh, gravitational energy. Not capturing the it. It is something related to the gravitational energy aspect. And Aqua and Terra, this is about the MODIS satellites I've spoken, which has a larger wavelength. So there are a fleet of satellites that NASA operates, and you have a lot of information about this. And coming to Earth, ESA, which is European Space Agency, there are even more satellites. SMOS, soil moisture related one, and then you have uh, this machine called Meteosat, which is Meteosat or the METOP, which is weather related satellites. and Sentinel, which operates in the Earth observation, which operates in the visible and infrared in visible region, and also in the SAR region, Sentinel 2 and Sentinel 5P. If you can see Sentinel 5P, Sentinel 5P operates in the pollution. It's more related to the pollution, and it can understand the particulates and all other information and meteorology. So in this way, there are a lot of satellites. I putting all the information regarding or the would be more congested. So I just here, I can just detail about the ISRO's missions. For natural resources and disaster management, you have resource set and reset. Resource set works in the optical region or the visible region, and reset works in the SAR. SAR, SAR as in synthetic aperture radar. Here you can see the features of it. It has 17 to 24 days repeativity, the reset satellite, and the resource set has 3-tier imaging with 56 meters, 23 meters, and 5.8 meters. So for the same place, you'll have different resolution of data. And Cartosat. Cartosat is like very much high resolution data. In Indian satellites, you have 60 centimeter data and even 28 centimeter data, which PAN. PAN says panchromatic, which means the image would be in only black and white. So it captures the entire region from visible region. As we already see the red, green, blue. When you narrow down the wavelength, so the amount of energy reaching to the sensor would be less. So when the energy would be less, you can't capture enough information that can be stored as a number. So what you do is that you will be covering a more area. So when you cover a more area, automatically the resolution reduces. You can see here for multispectral it's 1 meter, but for PAN you have 28 centimeters, which means when you allow all the energy in the visible region from a 30 centimeters region, it can be stored. It can be created as an image. But when you split it in only in the red band, you can't see it. You can't understand. You can't get enough information from 30 centimeters. So you have to increase the spatial resolution to get strong radiation. The reflected radiation, strong radiation. Since they're at hundreds of kilometers, the radiation should travel there. While traveling, there's a lot of interaction with the atmosphere happening. So all the spatial resolution or the spectral resolution are somehow indirectly linked. And going, this is how we can relate to it. Lesser the spectral resolution or spatial resolution and how it can be done. This is about Cartosat, and there is one more satellite. In the starting, I shown you a red color image of Earth showing, which is from Ocean Color Monitor. So this is one thing, and Saral. Saral is an altimeter or a radar thing which you can understand at what height the water or altimeter, altitude as height. You can understand the water surface level. You send by microwaves from the satellite, you reflect it back, and based on the time you calculate at what height, and based on the satellite altitude and the sensing time and the height, you get at what level the water. When water level is fluctuating, let's say a river or a reservoir is having different levels, so you can understand this as well. Reservoir monitor. There are a lot of applications with this kind of data. And INSAT, coming to this has an imager, 6-channel imager and 19-channel sounder, and this works in both visible infrared and also microwave in all the regions. So this is a weather satellite, and this is placed at 30. This is a geostationary. This is a geostationary satellite. So we are getting 48 images per day. And one kind of disadvantage is that once a geostationary satellite is launched, it only looks for a particular area. You can't get any other areas. So this is this remote sensing missions. And these are a few snapshots from a LinkedIn post I made some time ago. You can see how the ISRO program has evolved. In the starting, they started with IRS 1A and 1B. They launched, and with successful. When these were successful, they implemented with more generations of IRS satellites, and then these satellites they were successful. They were successful because they outlived the planned generation. Let's say if a mission was planned for 5 years, it has outlived, it has functioned for 10, 11 years. And then when the time came, when they said when the issues were getting more, they brought down back. But it has outperformed the expecting. In this way, when the IRS satellites were successful, they shifted to applications. For land and water resource applications, they designed resource set series. For ocean, they designed ocean set or INSAT. And for large scale mapping, cartosat. So this is how various Earth observation machines utilizing the different satellite sensors, or the specifications, the sensor characteristics, they're utilizing this, and they're understanding the Earth. So applications. So what all things we can application? What all applications we can do? Natural resources, agriculture. Remote sensing is very much vastly utilized for agriculture. Uh, in You can't discuss. I mean, at a space level, the application would be at a coarser resolution. You can't get in a very finer resolution. But agriculture or forestry, you can see degradation of forest land, or you can see coastal monitoring. You can understand how the coast has been reduced, or how the coastal changes have been happening. And global warming, you can understand ice and the studies of the sea. And in defense, surveillance, there are a lot of applications for remote sensing. And disaster response is one very important thing, because something happens, you can't really go there. You either have to fly a helicopter, and you need to get, if you need to get some real-time information, you have satellites up there which are looking at Earth, so they would send you the information. So disaster response in geosciences, hydrology, cartography, you have this data. We Applications can be of two types: one in real time, or you take the data, make use of it, make a product, and then you utilize it later. Let's say hydrology, you have digital elevation models. The elevation of each and every place on Earth is mapped with a 30-meter resolution. So an average height, let's say for a 30-meter area, the average height is mapped. So this can be utilized for many further applications, even wildlife conservation, marine conservation. Coming to maritime applications, you can identify algal blooms, or you can identify the chlorophyll content in the ocean. This is very much important to the coral reefs. So coral reef monitoring, oil spills. So the applications are numerous. What you can't see, satellite can see. You design a band, you launch it, and you do something. You do some research for this, and you can understand Earth in a very different way. And these are the applications in a broader way. I want to show you how Earth observation in real time is being used. A few case studies, and this is an example of South Lonak Lake. Uh, it's a global the lake outburst. If you can see in the starting, 17th September, the first image, it was full, and in September again it was full. But October we can see that this the the lake area is completely reduced, because the the lake has the lake has outburst, and it created a flash flood. What happened post is that there's a dam downstream of the glacial lake. You can see the A place, where there is A written, there was an existing dam. But with the huge sediments, the glacial lake has outburst, and all the water quantity from that top, it has come down, and it has completely washed away the dam. So there's no more dam remaining. This is, you can see on 10th May how the same place was looking, and 13th May. And this is a false color composite. That is the reason you see the vegetation in red color. The red color means the vegetation. You can see this is a false color composite. So when this glacial lake has burst, we can see how the effects have been. So in disaster management, this need not be in real time, but we can understand. This is not in real time, but we can understand how monitoring of the various things, and we can identify using Earth observation. Coming to real time application, we have the geostationary satellites, they can see, or even you can have the low Earth observation of the EOI-6. These are polar satellites, but they have captured the two twin cyclones on recent on 21st October, there were twin cyclones on both sides. On the Bay of Bengal, there's Hamoon cyclone, and on left edge, because with the higher wind speeds, and you're able to map the wind speed cyclones. So for disaster management, Earth observation is of very utmost importance. And with the advancement of machine learning and AI, the applications are becoming endless. Just for a few examples, in agriculture, you can see crop health monitoring. You can understand how the crop health. Let's say you is the crop good? Some pesticide or some pests have infected it, or what are the applications? The yield prediction. You can see the water quantity, you can see the growth of it, and you can predict how much the yield a farm can give an yield. Or you can do crop classification. Instead of going to the farm, you can just mapping it in a this thing. You can have the satellite images, and based on the spectral signature, or it's like the its behavior in different bands, you can do the crop classification as well. In this way, the applications are this is just an example in the agricultural field, but the applications are numerous. So one thing what I would want to conclude is that Earth observation has completely changed how we look at Earth. It's just putting in different filters. You put a visible, you put an infrared filter, you see the Earth in a different way. So you have hundreds of filters, hundreds of satellites flying there. You have a lot of information, and it is our responsibility to make this lot of information. And this has been, and Earth is being mapped from space since 1972. 1972, Landsat 1, the mission from US has launched, and then the Earth observation has started. NASA was the pioneer, and everyone followed, and now we have lots and lots of data. Now it is our responsibility to make use of this data, and how are we going to make this a better plan. So, and then signing off for today, Sushant, and thank you for being patient with me and listening for all this through this. And you, for any queries or any further discussions, you can always reach out to me. And opening opening up for the questions. Are there any questions? I see a couple of questions. Yeah, Ashish, I'll share the presentation. I'll share the presentation as well. And yeah, there's one more question. Uh, what are the materials used which sense such weather conditions and give them chromates or different symbols? Kalpana, if you are still there, you can unmute and you can speak.
Yes.
Yeah.
Yes, so sorry, I'm Niyati Trivedi. Actually, my question was that what are the actual materials which you use on the satellites which help us to detect the different weather conditions, and from that they interpret and colorize them so that we can symbolize to make it simpler
Mhm.
for common people. So, how is the whole thing, and what are the materials used, and how are they placed in the satellite?
Okay. So see, there are no specific materials placed.
Mm-hmm.
There is a sensor which detects. So only the sensor detects the sensor is made up of a different materials. Sensor making. To be very honest, I really don't know what material is made of a sensor.
Yeah.
I'll be honest. But once a sensor is made, you detect the energy. So the sensor it detects the energy. It says, okay, there is some X amount of energy coming. Once the X amount of energy is coming, that the satellite work is done. This information is sent to the ground, and then everything else is processing. The satellite only detects the amount of radiance or the energy that is reaching the sensor. Satellite captures only that energy. After that, this is completely changed into, the radiance is the radiance or the energy value is transformed to pixel or a digital number. Let's say I mentioned the radiometric resolution, right? Radiometric resolution. In the different values, you map it to a value, and then you put it out. So and then the image is generated. And if I can show it to you, I'll just show my presentation again and just reshare it. Is my screen visible?
Yes.
Mhm. So here, if you can see, uh, in this red band, here if I can move through this white, this has a particular pixel value 250.
Right.
White means 255. Black means
Okay.
0. So the value, the energy which is already there, it is being mapped into a pixel number 255,
Mm-hmm.
0 to 255. I'm saying 0 to 255 because it's on a 8-bit scale. If it's an 8-bit scale, you have 256 levels, 0 to ranging from 0 to 255. And once this information is mapped, you process this. Okay, if 255 is this. You have a few set of equations, which means the surface reflectance. So, and once all of these three are stacked, you get this kind of image. This image is surface so radiance, and there are different levels of processing. And what you're saying, right, to understand and to make it understandable for a common human or a common person. So it all depends on the level of processing. When you see a very raw image, you don't have any understanding. You just see a black and white, and let's say I'll give you an example of SAR image as well. If you can see this SAR image, you can see nothing. You just see some pixels, and if you zoom in, there's a lot of image noise as well. You have to remove the noise. So remote sensing is more very much less of the image capturing. It's more of image processing.
Processing, right.
So here in this session, I'm more focused on the how the physics of it. How remote sensing, how
Yes, the
satellites really
types
work.
of it and their importance, right?
Images and how you see it different way. We can the image processing and how
So
it's
the
a completely
processing is
different
the
thing.
most important part in the
Yes.
censoring part. So like how do you actually change the resolution of a particular camera or any other capturing
Mhm.
device you use? So how do you change the resolution of it or in
Mhm.
by changing the number of
Okay.
pixels in them?
Right. I understand. I'll just open up one presentation. I just have something. Just give me a moment. Yeah. So here, if you can see my screen, there is one thing here. You understand? Sorry. Yeah. You can see here. There is one particular satellite. This satellite is called GPM Core Observatory. Okay. This GPM Core Observatory. This focuses on. Sorry. Yeah. So this focuses. This has multiple information. This is this
Yeah.
microwave imager, and there is
Mm.
one. So you put multiple sensors. You put one microwave imager. You put one radar. You put radar in particular. See, this part of the radar focuses on this
So
particular
much of
wavelength, and this
many.
part of
Yeah.
radar. So you don't change resolutions. If you want n resolutions, you put n different sensors.
Sensor. Okay.
So
So they get processed by
you
different sensors step by step.
yes, so you get the information, and this particular information you have this and this information is relayed back to the ground stations and processed. And now the sensing has getting it is getting more advanced, such that you're just processing the data in the satellite itself. It's called onboard processing or edge computing. When it's edge computing, you do it on edge, on the satellite itself, and only send information, relevant information. So one thing I want to emphasize again on the resolution part is that if you
Yes.
want to change a resolution, you have to put out a different sensor. You can't change for a particular
Resolution of
sensor,
a particular
because
sensor. You have to like multiple
yes,
sensors will process it step by step.
yes, yes. Mhm.
Thank you so much. It was a really great informative session. And thank you for clearing
Yeah,
the doubt as well.
it's a pleasure. Yeah, any other questions from other one? You can have the question.
Hi Sushanth.
Hi.
Hi Sushanth. I'm
Mhm.
Samuel.
Mhm.
I have used Sentinel-2 Landsat 8 images for yield
Mhm.
estimation, yield prediction, rainfall prediction, everything.
Okay.
But now I want to use to find greenhouse gases from particular
Mhm.
places from
Mhm.
agriculture fields.
Okay.
So can you suggest any particular satellite image? It will be help for greenhouse gases finding
Sure.
with low
There are
resolution.
one thing I'll tell you again. See, this low resolution
Um,
is low resolution. You mean you want greater, let's say 1 meter or 2 meter. You want it at a
yeah, exactly.
yeah. That it's not low resolution. It's high resolution. Lower pixel size, but high
Okay,
resolution.
sorry.
Yeah, it's a high resolution
Yeah,
image.
sorry.
So one thing I want to
Mm.
tell you is that say the satellites are sensing at higher altitude, and greenhouse gases are something very weak. The gases, when they travel in the atmosphere, they move up. they completely they diffuse, they interact with other atmosphere. So for a smaller place, let's say you want in a 10 meter or 30 meter by 30 meter place, you can't get the strong radiation. See,
Okay.
even for a satellite to detect a very strong way, in a
Mm.
even for the satellite to detect the radiation, you need some strong radiation. You can't have a weak radiation, because this, by the time it reaches
Exactly. Yeah.
from it completely disappears. So the wavelength, the energy attenuation is means reduction is there. So
Yes.
what I can suggest is
Mm.
that you can't really get uh, the at higher resolution for from space for the greenhouse gases. But the technology is improving. Recently we had one satellite called methane sat. They designed the satellite
Okay.
to look at particular places on the earth, not particular places, on only focusing on oil and gas explorations. You have this drill sites, right? Drill sites, as in on
Yes.
onshore,
Yes.
offshore
Mm.
oil exploration in Dubai and everywhere. You have this lot of sites. So these are the main contributors for methane. So the satellite named Methane Sat, it is focusing come more on this images, and this is how the Methane Sat would be. So I'll just show my screen on the Methane Sat. So for the methane side, it has this pixel. See, this is how methane. This is one example for methane. So there are the satellites which has the pixels. Like, see, you understand, right? 7
Yes.
kilometers to
Yes.
5.5 kilometers. Very huge resolution. But this particular satellite now, it is able to map the point source as well. But the one
Okay.
minus point is that it doesn't map the entire Earth. It maps only particular locations. And there are
Yeah.
some
Yeah.
other
Exactly.
satellites
I
as well.
want. I also want this only.
Ha ha ha. Right,
From
right.
latitude, longitude, I have ground truth data. Means I want to take
Mm-hmm.
ground truth data. From that ground truth data, I want to classify different fields. Means X, Y, Z, different crops are there. From that, how
Mm-hmm.
much gas will be emitting? Like that, I want
Right, right.
to study. So
Okay.
I think so. This satellite will helpful. I think
Mm-hmm.
maybe it is
Sure.
freely available or
Mhm.
not.
No, this data is not available yet. This data will be getting in early 2025. This has very recently launched. This has very
Okay.
much recently launched, and you'll get the data later. So maybe we can take this on a one-on-one discussion. You can reach out to me on LinkedIn. We can have a one-on-one meeting. So this is not the proper place, to discuss in it. This
Okay.
is not
Okay.
the
Okay.
proper place to
Thank you.
discuss
Thank
it longer. I'll open
you.
the forum for other questions as well. Reach out to me on LinkedIn or my
Thank you.
email ID. We can sure have a discussion. Yeah,
Okay, okay, definitely.
yeah, yeah. Any other questions from people on the call? Uh, so looks like there are no more questions.
Yeah, it seems like that.
Yeah.
Because before ending the session, I would like to say a few words. So,
Mm-hmm.
guys, if you are really interested in aerospace, then you can join our aerospace community, Hexstar Universe Aerospace Community. I'm giving you the link. You can join over there. And for more interesting sessions like this, you can follow up there, or I'll be giving you a link for the next session. You can also sign up there also.
Hi, actually, I wanted to ask
Mm-hmm.
I'll be starting my B.Tech in aerospace engineering this year.
Mm-hmm.
So, is there in the aerospace community group, like, will there be any such internships or any some programs in which we can participate and also gain experience and have an internship kind of thing also in your first year or any year? Something that way. So, is it
Yeah,
available?
we do have an internship program, but
Uh-huh.
this we conduct two internship programs. One is in the summer and one in the winter. The summer one, it is
Right.
already nearing the end, so you can join the winter session.
Sure, I will. That would be interesting.
So I don't think there are any more queries.
Mm-hmm. Yeah. So a few concluding notes from me. On concluding note, I'll just try to share the PPT to the team so that they can mail it over, or you can reach out to me personally as well. I've shared my email ID in the comments in the chat. You can reach out to me on my email as well. I can share you the PPT, or I'll share it to the team. They can send it over mail to everyone. Yeah.
Yeah, as you like.
Mhm. Yeah, that's it. That's it from me. Thank you very much for being very patient to audience, and hope you like this session. Yeah.
Yeah. Thank you.
Yeah, thank
It
you.
was a
Thank you.
wonderful session. And thank you everyone else
Mhm.
for joining. Good night.
Yeah. Good night. Bye bye.